Hi. So, continuing on from my previous video where we stopped on common support assumption, now we'll continue on and talk about correlation and causation in this video. This video may be a little heavy on the for calculations related to expectations, but I hope to go through it slowly so that it makes sense, and we will tie it up to the main topic and the intuition in every step of the way. So firstly, we are going to ask a simple question to clear up this randomization assumption. So does this is the question we have in mind. Does the potential outcome being independent to treatment assignment mean that the observed outcome is independent of treatment assignment? Now think about it, what that means intuitively, and think about what its answer is also intuitively. The question is asking, just because the potential outcome of the observation is independent of what sort of treatment group they are in, does that mean the observed outcome will differ no matter what treatment group they are in? The answer is no. It's a big fat no, because it does not necessarily mean that, because the observed outcome, we would ideally like to see that there is a treatment effect, right? So ideally, when the treatment assignment changes, there is an observed difference in the outcome. The potential outcome would have been the same, but in the real world, there is a difference because the treatment was assigned, right? So that's ideally what we want to conclude from a randomized control trial. But let's try to prove this more mathematically. So firstly, I will let's calculate the expectation. Let's calculate the expectation of the observed outcome. Oh, where did I go? Yeah, let's calculate the expectation of the observed outcome times the treatment assignment. So we are trying to see if this value is independent or what this value is, right? So if this is independent, of course, if independent, this would be the same as this, right? We would be able to multiply these values individually if independent. Caveat, right? But let's check if that's true. So the expectation of yi times di, we can write this as the expectation of yi times di in the subgroup of treatment times the probability of being assigned treatment plus expectation of yi di in the subgroup of control times the probability of being assigned control. Okay. So this is true because we are just segregating the whole group as treatment and control, and we are just calculating the probabilities here, right? Now look carefully at the second term. If di is equal to 0, this whole term will become 0, and essentially this whole term goes to 0. So we can directly write that the expectation of yi di is simply just our first term. It's the expectation of yi di in the treatment subgroup times the probability of being assigned the treatment subgroup. Okay. Now let's further decompose this. So remember here that we can try and introduce the function that we defined quite a few classes before, the function of the observed variable as a function of the potential outcomes. So let's try to write that. So let me copy it. Yeah. So let's use this assumption, this function, and rewrite our expectation. So I'm going to write it on the side here. Oh, sorry. Yeah, I'm going to write it on the side here. So the expectation, now that we have a whole yi here, is equal to di times yi of potential outcome plus 1 minus di times yi of the potential outcome of not treated. This whole times di conditional on di being equal to 1 times the probability that di is equal to 1. Now a lot of things can be reduced here. So firstly, di is equal to 1. So this is 1 and this term here is 1, and that means this term here is 1 as well, which means this whole term is 0, which means we can simply rewrite this whole thing as expectation of the potential outcome of being treated conditional on the treatment group times the probability of being treated. Okay, so I hope this makes sense. Now since we have the assumption, here we have our assumption that the potential outcome is independent of treatment assignment, we can simply rewrite this as expectation of yi potential outcome of the treatment group times probability of being assigned treatment. Okay, now we'll do one last neat trick here. This probability of being treated can be written as the expectation of being treated times times the number of times you get treated. So it's like an indicator function. Okay, so we are just rewriting probability in as a expectation. So it's the expectation, it's the average of being treated times whether or not you are treated. So this is like a binary value taking variable, and this variable will be equal to 1 because you are being treated. So that means we can write probability of di equal to 1 as just the expectation of di equal to 1. So we rewrite this whole equation as expectation of potential outcome times expectation of di equal to 1. Okay, so that is the math part of it. Now what did we primarily conclude? We conclude with all our calculation that expectation of yi times di is actually equal to the glitched again. It's actually just equal to the expectation of the potential outcome of being treated times the expectation of the dummy variable. Okay, now what did we say? We said that if this expectation of yi di is equal to expectation of yi times expectation of di, then if this is true, then yi is independent of di. Yi, again, here it's observed outcomes, it's different from potential outcomes. So what would be necessary for this statement to be true? We would want that the expectation of the potential outcome is equal to the expectation of the observed outcome. Now if that's true, so if that's true, then the observed outcome is independent of treatment assignment. But this also means there is no treatment effect. There is no treatment effect. Why? So think about it. If the potential outcome of being treated, which is just for one subgroup, if that is equal to the observed outcome of the whole subgroup, then it means there was no treatment effect at all. A way I can show this mathematically is that the expectation of the observed averages is simply equal to the sum of the expectation of the potential outcome of the treatment group and the expectation of the potential outcome of the control group divided by 2. It is supposed to be the average of the two. So if you have a group, the total group average is the sum of these individual averages, right? That makes sense, right? Now if that's true, if this is true, then I can rewrite this equation as correct. Now using some simple algebra, we can conclude that this also means expectation of yi will be equal to expectation of yi of 0, which means further that expectation of yi is equal to the potential out expectation of yi of 1, which is equal to the expectation of yi of 0. That's saying that the average effect observed on the entire group is the same as the individual averages of those two groups. That's saying that the treatment and control groups are not different on average. They are the same. They have the same expected outcomes. That means the treatment failed. There is no effect on the treatment. Okay. So that is why in randomization, it is not necessary that because the potential outcomes are independent of the treatment assignment, that the observed outcome will also be independent of the treatment assignment. Okay. So I'll pause here. I was thinking of continuing about correlation and causation, but I will add it in the next video.